Dear students, I hope you're all utilizing these holidays properly for the revision of the subjects. Now, we have started Unit 5 in our classroom last month and we have completed two sections, Section 65 and Section 66. There are two more sections to be completed in this unit, that is Section 67 and Section 68. Now, we study here Section 67 that deals with the spectrum. This Section 67 I will be presenting as 2 or 3 presentations as part 1, part 2 like that. Okay. So this is part 1. What are the contents in the part 1? This first part of Section 67 consists of certain definitions and a main and a result. Okay. The definitions are spectrum of an element X of a Banach algebra A. Then the spectrum sigma of X is a subset of the closed disk in the complex plane. Then we are going to see resolvent set of X and then resolvent of X. Finally, we will derive the important relation known as resolvent equation. Definition. For any operator T belong to B of H, spectrum of T, that is sigma of T, spectrum of an operator, that is sigma of T, is defined to be set of lambda such that T minus lambda I is singular. In other words, sigma of T equal to set of lambda such that determinant of T minus lambda I equal to 0. Next, definition, spectrum of an element X of the Banach algebra A. Similar to the spectrum of an operator, we can define spectrum of an element X of A. Spectrum of an element X belong to A is defined by sigma of X is equal to set of lambda such that X minus lambda 1 is singular. Clearly, the lambda which satisfies X minus lambda 1 is singular or the elements of sigma X, they are all complex numbers. So sigma X is a subset of the complex number system or subset of the complex plane C. Now we know that the function which takes from the scalar lambda to the vector x minus lambda I is continuous, and we have already proved that the set of singular elements S is closed. S is nothing but the complement of G, where G is set of regular elements which is open. G is open, and so being the complement of G, S is closed. Hence, S is closed containing singular elements. Sigma of X contains scalar so that X minus lambda is singular, and also the mapping which takes from lambda to X minus lambda is continuous. We can say sigma X also closed in C. Now, we shall next prove that sigma X is a subset of the closed disk. Set of Z such that mod Z less than or equal to norm X. Okay. See the diagram. This is the entire complex plane in which we have chosen this to be the origin. Let us take an element that is vector X here. So the length from origin to X is norm of X. Then we have the corresponding closed disk here, inside which any element isn't belong to the circle. Inside the circle will satisfy mod Z less than or equal to norm X. Okay. We can prove that sigma of x is a subset of the closed disk Z such that mod Z less than or equal to norm x. If possible, we shall assume on the contrary that there exists a complex number which does not satisfy this inequality. Okay, to show that, we have to show that sigma of x is a subset of this one. So if it is a subset of this one, all complex numbers in sigma x will satisfy the inequality. Okay, but to show this, we prove by contradiction, that is, if possible, assume that there is at least one complex number lambda in sigma of x such that the opposite inequality holds, that is, modulus of lambda is strictly greater than norm x. If modulus of lambda is strictly greater than norm x, we can take this to the right hand side, then it will become 1 greater than norm x by mod lambda, okay, or 1 greater than norm of x by lambda. That is, otherwise norm of x by lambda less than 1. Okay, norm of x by lambda less than 1. Here we can add 1 and minus 1. We can add 1 and subtract 1. 1 minus 1 will not change the result. So we can add 1 minus 1. So if we bring negate minus inside, minus 1 minus of minus plus x by lambda. 1 minus 1 cancels to give x minus lambda only. So norm of x minus lambda is written as 1 minus x by lambda, which is strictly less than 1. Okay. But we have already seen in section 65, the first theorem 65a, which states that in a Banach algebra, if norm of 1 minus x less than 1, then the element x is regular element. Okay. If it is so, in place of x we have 1 minus x by lambda, such that 1 minus of that element is less than 1. So this element, that is 1 minus x by lambda, should be a regular element, that is regular, by theorem 65a. Then we can cross multiply this, that is lambda into 1 minus x is regular, or we can multiply by another minus 1, whatever it is. Otherwise, which can, if lambda into 1 minus x is regular, clearly x minus lambda 1 is also regular. Okay, but this is a contradiction, because you know lambda is in sigma of x, where sigma of x is the spectrum. That is, if lambda is in sigma of x, by definition of sigma of x, x minus lambda into 1 is singular. But we arrived at x minus lambda 1 is regular. So this is a contradiction, because x minus lambda 1 is singular. This contradiction arises because of our assumption that there is a lambda which satisfies mod lambda greater than norm x is wrong. So we must have mod lambda should be less than or equal to norm x for every lambda in sigma of x, or mod z less than or equal to norm x for every z in sigma x. So clearly we have shown that sigma of x is a subset of the closed disk in the complex plane, that is set of z such that mod z less than or equal to norm x. Now we shall see a note here. Since sigma of is a subset of the closed disk, just now we have proved, clearly it is bounded. Okay. Thus sigma of becomes a closed and bounded subset of C. Hence, by Hien-Borel theorem, sigma of x is compact. What does Hien-Borel theorem say? Any closed and bounded set in Rn or C power n, R power n or C power n is compact. Okay. Here sigma of x is a closed and bounded subset of C power 1. C means C power 1. Hence, by Hien-Borel theorem, this should be compact. So sigma of x, that is nothing but spectrum of an element x defined by set of z such that, set of lambda such that x minus lambda 1 is singular, is a compact subset of the complex plane. Next we go for the definition of resolvent set of x. Resolvent set of x is different from resolvent of x. Resolvent of x is a function, whereas resolvent set of x is a set. Okay. Resolvent set of x is nothing but the complement of the spectrum. So the complement of sigma of x is called the resolvent set of x, which will be denoted by rho of x. So what is rho of x? Rho of x is sigma of x whole complement. Okay, or sigma of x will be rho of x whole complement, whatever it is. Okay, so sigma of x and rho of x are complements to each other. Since sigma of x is a closed subset of the closed disk we have just now proved, it follows that rho of x is an open subset of C. Okay, because rho of x is the complement of sigma of x, because sigma of x is closed, rho of x should be open, which contains the set of z such that mod z greater than norm x. Okay, because sigma of x is contained in set of z such that norm z less than or equal to norm x, but rho of x is the complement of sigma of x. So it will contain set of z such that mod z greater than norm x. Okay, if we, sigma x means mod x less than or equal to norm x, whereas considering rho of x will contain the subset that is set of z such that mod z greater than norm x. Okay. Next we see definition of resolvent of x. The resolvent of x is a function from rho of x, that is resolvent set of x, to the Banach algebra A, rho of x to A, defined by x of lambda equal to x minus lambda 1 power minus 1. Resolvent of x is a function defined by x of lambda is equal to x minus lambda 1 power minus 1. Okay, here the lambda belong to rho of x, whereas the right hand side belong to is a vector belong to A. So the function x takes an element of rho of x to an element of the Banach algebra, that is defined by x of lambda equal to x minus lambda 1 power minus 1. Okay, we have already shown the same theorem, that is 65C, which clearly states that x of lambda is continuous. Now x of lambda equal to x minus lambda 1 power minus 1. Take lambda outside here. If you take lambda outside, it will be lambda power minus 1, lambda divided by lambda. So x by lambda minus lambda by lambda will be 1 power minus 1 for lambda not equal to 0. Okay. Here you have, this is constant lambda power minus 1, otherwise 1 by lambda, which is constant, whereas this part is a vector. Okay. So scalar multiple of a vector. Right. Clearly, as lambda tends to infinity, if the particular complex, if the complex number x tends to infinity, we see that 1 by lambda tends to 0. So 0 into this vector is 0. So the right hand side tends to 0 whenever lambda tends to infinity. So left hand side, that is x of lambda, also tends to 0 as lambda tends to infinity. Now we shall derive what we call as a resolvent equation. Okay. This is an important equation which will be used to prove the main theorem of this section, that is otherwise sigma of x, the spectrum of x is a non-empty subset of C. Okay, or spectrum of x is non-empty. To prove that result, we need the resolvent equation. So how to derive resolvent equation? To derive resolvent equation, let us take two scalars lambda and mu in rho of x. Okay, rho of x is nothing but what? Rho of x is a resolvent set of x. Okay, which contains set of z such that mod z greater than norm x. Right. Now x of lambda equal to x of lambda into x minus mu 1 into x minus mu 1 power minus 1. Here x minus mu 1 is a vector and its inverse. So vector and its inverse will be 1 into x of lambda, the same x of lambda. So x of lambda can be written as x of lambda into 1. In place of 1, we can put x minus mu 1 into x minus mu 1 power minus 1. Okay. That is equal to x of lambda as it is, x minus mu 1 as it is. This by definition, x minus mu 1 power minus 1 equal to x of mu. Okay, because we have defined x of lambda to be x minus lambda 1 power minus 1. If x of lambda is x minus lambda 1 power minus 1, x of mu will be x minus mu 1 power minus 1. Okay. That is x of lambda, x as it is, minus mu 1 here, minus mu 1. Now we add and subtract minus mu 1 into plus mu 1. Okay. So we are adding lambda into 1, subtracting minus lambda 1 plus minus mu 1 as it is here. So if you expand this clearly, this minus lambda 1 plus lambda 1 will get cancels to give x minus mu 1, the same thing. Okay. So x minus mu 1 is written as x minus lambda 1 plus lambda minus mu into 1 into x of mu as it is. Okay. Now we take this inside, that is x of lambda into the first vector x minus lambda 1 plus this is scalar lambda minus mu into the vector is x of lambda into 1 is x of lambda into x of mu. Okay. But you know, x of lambda by definition nothing but x minus lambda whole power minus 1. Okay. X of mu equal to x minus mu 1 whole power minus 1. Similarly, x of lambda will be x minus lambda 1 power minus 1. So x minus lambda 1 power minus 1 into x minus lambda 1 means in inverse and the vector will give 1. So 1 plus lambda minus mu into x of lambda into x of mu. Okay, by definition of x of lambda, which is equal to x minus lambda 1 power minus 1. Okay. So that is equal to x of mu plus lambda minus mu into x of lambda into x of mu. So finally we have proved that x of lambda equal to x of mu plus lambda minus mu into x of lambda into x of mu. Take this to the left hand side. So x of lambda minus x of mu will be equal to lambda minus mu into x of lambda into x of mu. Okay. This equation is usually called as the resolvent equation. That's all for this part 1. Thank you.